Welcome to Understand the Math. In the video description, you'll find a link to free guided notes that can be downloaded and filled in as you follow along with the video. This video is the third part of a 7-part series on topics that commonly appear on an introductory linear algebra midterm or final exam. The topics in this third video focus on content related to linear transformations. In the future, I plan on posting more in-depth linear algebra videos, but I wanted to begin with this overview series of basic topics. We'll begin by defining the domain and codomain of a linear transformation. Rn is the set of all n tuples of real numbers. Rn can be written in two ways. The first way that it's written here is called column vector form. And the second way that it's written here is called comma delimited form. A transformation in linear algebra is the operation of changing one vector into another vector. And a vector is just an n tuple of real numbers. Let's look at an example of this. In this example, x is transformed into t of x. Let's draw x and t of x. X is -1 units in the x1 direction and 2 units in the x2 direction. So -1, 2 gives us a vector that looks like this. And we'll label that as vector x. Our t of x is 5 units and 2 units. So 5 in the x1 direction and 2 in the x2 direction. And this gives us a vector t of x that looks like this. So we can see that when x is transformed to t of x, it is rotated and it's stretched. In order to determine the domain and codomain of a linear transformation, we need to consider a transformation from Rn to Rm. This is our most general transformation. In the example above, both x and t of x are elements of R2. So the transformation went from R2 to R2 and didn't change dimension. Now we're going to look at a more general transformation that can change dimension as it goes from Rn to Rm, but let's keep in mind that m could equal n. In the picture here, we see that x is transformed into a of x or t of x. We can write this in another way. We can say that a times x, instead of writing t of x, we can say that that's equal to b. Now let's look at the size. A is going to be m by n, which means x, because it's a vector, has to be n by 1. It has to be n because these middle numbers need to match up. And it's 1 because it's a column vector. And that's equal to b. If we cross out these, what's left is m by 1, and that's the size of b. So we can say that x is an element of Rn. That's x. And then we can say that b is an element of Rm because that's b. This then tells us that Rn, because x is an element of Rn, Rn is the domain of our transformation. And then B is an element of Rm. B is the same as T of X. So Rm is called our codomain of our transformation. Let's now use these definitions to find the domain and codomain of a linear transformation given here, where we're given a matrix A. We'll start by writing down A of X is equal to T of X, and we'll write down the size of A. So the A that we're given has 2 rows and 3 columns, so it's a 2 by 3. Which means X has to be a 3 by 1. We'll put an X under there so we know that's what we're talking about. And then the 3's are going to cancel, and we're going to be left with a 2 by 1, which is our T of X. Let's make a note that X is an element of R3, and T of X is an element of R2. So that means our domain, which is related to X, our domain is equal to R3, and our T of X is related to our codomain, so our codomain is equal to R2. Let's now talk about how to find the standard matrix of a linear transformation. We'll begin by defining standard basis vectors. Standard basis vectors serve as fundamental building blocks for understanding vectors that are used to form the columns of matrices, such as a matrix A, when working with transformations. The standard basis vectors for R2 are E1 and E2. E1 and E2 are the columns of I2, which is our identity matrix that looks like this. And so we can say that I2 is E1, E2. If you've studied physics, these are the same as what you might be familiar with called I hat and J hat. Our standard basis vectors for R3 are E1, E2, and E3. These vectors are the columns of I3, which looks like this. So this is E1, E2, E3. All vectors in Rn are expressible in exactly one way as a linear combination of the standard basis vectors. Let's see what that looks like. If we have a vector x given here, x1 through xn, so x is an element of Rn, like we've seen before, it can be written in terms of the standard basis vectors. So we would write it as x1 times e1 plus x2 times e2 all the way up through xn times en. We can now use our standard basis vectors to find the standard matrix for a linear transformation. If we have a linear transformation that transforms vectors in Rn to vectors in Rm by T of x is equal to A times x, our standard matrix is given by A is equal to T of E1, T of E2, all the way up through T of En. I would suggest that you memorize that because often students struggle with remembering what is a standard matrix for a linear transformation. Let's now look at two example problems. For our first example, we're asked to find the standard matrix for the linear transformation given here. Our standard matrix is A from T of X is equal to A times X. So what we need to do for this problem is we need to break apart the transformation into an A times an X. So we say that T of X1, X2 is equal to, and if we break apart that right there, we end up with a 2 minus 1, 1, 1 times X1, X2. So that provides us our matrix A, and we can write that our standard matrix is equal to 2, 1 minus 1, 1. Let's now look at our second example. In our second example, we're asked to, again, find the standard matrix for a linear transformation, but now we're given very different information. In this problem, we're given two vectors, 1, 1 and 2, 3, and we're given their transformations. So what we're going to have to do is we're going to have to back out what A is based on how these two vectors are transformed. So let's remind ourselves that A is T of E1 and T of E2. What's going to help us in this problem is if we label the vectors that were given. So our first vector 1, 1, I'm going to label as V1. And then our vector 1, 2, this is going to be T of V1. Our vector 2, 3 is V2. And our next vector is going to be T of V2. And that's going to come in handy when we do some calculations. The idea is that we're going to use how V1 and V2 transform to find how E1 and E2 transform. Because A is T of E1 and T of E2, so we need to know how these vectors transform. This is a very complicated linear algebra problem. When I'm doing the linear algebra review for a final exam, this is a problem that students always want to see because I think it's one of the most challenging problems. So I have created steps that we can follow just to make it a little bit easier. Our first step is that we're going to write V1 and V2 that we defined above in terms of E1 and E2. So let's go ahead and let's do that. So V1 is 1, 1. As we saw on the previous page, our vector can be written as a linear combination of our standard basis vectors. So this is C1 times 1, 0, which is our E1, plus C2 times 0, 1, which is E2. This is going to equal 1, 0 plus 0, 1, because we need to make it equal to 1, 1. And these vectors are E1 plus E2. I wanted to go through a lengthy explanation of this, but in practice, you can go right from this vector to this set of vectors by just breaking it apart into its components. And I just realized I didn't write that as V1, so let's add a V1. Likewise, V2 is equal to 2, 3. And we can write this as 2E1 plus 3E2. The second step is that we're going to write T of V1 and T of V2 in terms of T of E1 and T of E2, and then we're going to solve for T of E1 and T of E2, and that way we can find A. We're going to write V1 as E1 plus E2. That's what we found on the previous page. And we're going to take the transformation of that vector. So T of V1 is going to be T of E1 plus T of E2. And if we look back at the previous page, that is equal to vector 1 minus 2. That was given to us in the original problem. Now we can write V2 from the previous page, and we got it equal to 2E1 plus 3E2. Now let's take the transformation of that. So T of V2 is 2T of E1 plus 3T of E2. And that is equal to the vector that we were given originally, minus 2, 5. Let's label these two equations as number 1 and number 2. If we look at these two equations, we can see that we have two equations and two unknowns. Our unknowns are T of E1 and T of E2. What we're going to do is we're going to solve for T of E1 in the first equation, and then we're going to substitute that into the second equation. So for number 1, we're solving for T of E1. So T of E1 is going to equal 1 minus 2 minus T of E2. And we're going to throw that into our second equation. In our second equation, we have 2 times T of E1. We'll substitute in 1 minus 2 minus T of E2 plus 3 T of E2, and that's equal to minus 2, 5. We now need to solve this for T of E2. So we have 3 T of E2 minus 2 T of E2. So that gives us T of E2 is equal to minus 2, 5. And then we'll take the vector on the left, put it on the right. So we have a minus 2 times 1 minus 2. And if we compute that, we end up with a minus 4 on top. And then a 5 plus 4 gives us a 9. So we have T of E2. Now we're going to find T of E1. So T of E1 is going to be 1 minus 2 minus a minus 4, 9. And that gives us a 5 and a minus 11. We can now use this information to find A. So let's go back and let's box our answers so we can find them. So there's our first one. There's our second one. Let's now write down what A is. So A is T of E1, T of E2. So we'll grab the T of E1 first, and that's 5 minus 11. And then T of E2 is minus 4, 9. So now we have a matrix that will enable us to transform any vector in the same way that it transformed the two vectors that we were given at the beginning. For a nice check is we can take this matrix, multiply it by one of our vectors, and see if we get the transformation. So let's do that. So let's take 5 minus 11 minus 4, 9, and let's multiply it by our vector v1. And this is going to give us 5 minus 4, which is 1, and then minus 11 plus 9 is minus 2, and we can verify that that is indeed t of v1. The next topic in our review is matrix transformations. We'll begin with transformations that can be used to reflect vectors about the x-axis, the y-axis, and the origin. In the picture, we have a vector xy, and we're going to reflect it about the x-axis. When we do that, the vector looks like this, and it becomes x minus y. To understand how we find the transformation that will reflect xy to x minus y, we need to reflect E and E2 about the x-axis. E1 lies along the x-axis, so it's going to stay the same. However, E2, as we reflect it about the x-axis, will become like this, and it can be written as 0 minus 1. The transformations of E1 and E2 are going to form our standard matrix. A is equal to T of E1, T of E2. And these transformations form the columns of matrix A. So we put this in. T of E1 was the same as E1, so that's 1, 0. And T of E2 became 0 minus 1. We have to make sure to write these vectors as columns. So this matrix will reflect a vector about the x-axis. Let's see how that works. In our example, we have A times the vector 1, 1. So if we plug in our standard matrix, 1, 0, 0, minus 1, and we multiply that by our vector 1, 1, we end up with the vector 1 minus 1, which is the vector reflected about the x-axis. To find the standard matrix for the reflection about the y-axis, we do something very similar. We're going to reflect E1 and E2 about the y-axis. E1 is going to come over here, and it's going to be given by minus 1, 0. And E2 lies along the y-axis, so it's going to stay the same. So A is again T of E1, T of E2, and that is going to equal minus 1, 0 for T of E1, and then T of E2 is the same as E2, and that's 0, 1. To find the linear transformation for a reflection about the origin, we're going to reflect E1 and E2 about this line x1, x2. So what's going to happen is they're going to swap places. E1 is going to go to E2, and likewise E2 is going to go to E1. So our matrix A is going to look like this. T of E1, which is now 0, 1, and then T of E2, which is 1, 0. Let's now find a standard matrix A that orthogonally projects vectors onto the x or the y-axis. When we project a vector onto the x-axis, our vector xy becomes our vector x0. When we project E1 and E2 onto the x-axis, E1 stays the same, and then E2 just goes down to the origin, which is 0, 0. So our A is T of E1, T of E2, and that's equal to T of E1, which is just E1, 1, 0, and then T of E2 is our origin, 0, 0. Similarly, to find the linear transformation for an orthogonal projection onto the y-axis, we're going to project E1 onto the y-axis, so it's going to go to the origin, and E2 lies along the y-axis, so it's going to stay the same. So A is T of E1, T of E2, and this is equal to 0, 0, and then 0, 1. This next matrix transformation is much harder than the other ones. This transformation is a rotation, and we're going to find the standard matrix that rotates vectors counterclockwise. Let's underline that. About the origin through an angle theta. Let's focus now on our vector xy. This vector is going to be rotated through an angle theta, and it will transform into vector w1, w2. So we can say T of xy is equal to w1, w2. To find the standard matrix for making this transformation, we're going to see how E1 and E2 transform. E1, as we rotate it through an angle theta, is going to become cosine theta, because that's the x component. Think of it like this. This is the x component and the y component, and we know from trigonometry that the x component is cosine theta, and then the y component is sine theta. Then we go up and we look at E2. E2 is going to transform to T of E2. And if we look at that, the x component is going to be minus sine theta. And notice that's our theta. And then the y component is going to be cosine theta. This allows us now to write down our standard matrix for this transformation. So A is T of E1, T of E2. T of E1 we found was cosine theta, sine theta, and we again writing it in columns. And then T of E2 was minus sine theta, cosine theta. So that is the standard matrix that rotates vectors counterclockwise about the origin. We could do a similar analysis for rotating clockwise about the origin, and if we do that, we end up with this matrix transformation. We have cosine theta minus sine theta, and then sine theta, cosine theta. The last matrix transformations that we'll look at are contractions and expansions. When we contract a vector horizontally, our standard matrix looks like this. It's K0, 0, 1, where K can be greater than 1 for an expansion, and K is between 0 and 1 for a contraction. Let's see how this works. So say we have a vector 1, 1, and we want to expand it horizontally by a factor of 2. We would put K equal to 2 in our matrix, multiply it by 1, 1, and we would end up with 2, 1. So what happens is our vector expands horizontally by a factor of 2. The vertical contraction and expansion is going to be very similar. For this one, our standard matrix looks like this. We have a 1, 0, and then a 0, K. When K is bigger than 1, we again have an expansion. And when K is between 0 and 1, we have a contraction. If we have our vector 1, 1, and we want to expand it vertically by a factor of 2, our K gets set equal to 2. We multiply A times 1, 1, and we end up with a 1, 2. And if we plot that, you can see that our vector expands vertically by a factor of 2. Let's now look at an example that combines some of the matrix transformations that we've just gone over. In this example, we want to find the standard matrix of the linear transformation that reflects across the y-axis, then rotates by pi over 4 radians counterclockwise, and then stretches vertically by a factor of 2. So the stretching is the same as expansion. We have to do this in 3 stages. The first matrix is the one that's going to reflect across the y-axis. That's from our previous page. Then we have a rotation. So I've written down our rotation matrix for counterclockwise rotation. Now what we have to do is plug in pi over 4. So this is cosine pi over 4, sine pi over 4, minus sine pi over 4, and then cosine pi over 4. We can now remember that sine and cosine of pi over 4 is root 2 over 2, so let's plug that in. So this is root 2 over 2, root 2 over 2, minus root 2 over 2, and root 2 over 2. Our last transformation is a vertical stretch by a factor of 2, so our K gets replaced with 2, and we have 1, 0, 0, 2. Our A is going to be equal to our third matrix times our second matrix times our first matrix. And I know this might seem backwards, but what is happening is that we do our first transformation, then our second transformation acts on that, and then our third transformation acts on that one. So let's go ahead and let's number these 1, 2, 3, so we can see which one is first, which is second, and which is third. So our A is equal to our third one, 1, 0, 0, 2, times our second one, which is our rotation 1, and then times our first one, which was our reflection. When we multiply these out, we end up with this matrix. And that is the matrix that we would use to take a vector, reflect it across the y-axis, rotate it by pi over 4 counterclockwise, and then stretch it vertically by a factor of 2. And it's really nice that we can do all 3 of these transformations with just one matrix multiplication. The last topic in this review is one-to-one and onto transformations. If we have a transformation that is one-to-one, distinct vectors x have distinct images t of x. That means that ax is equal to t of x or b has a unique solution. And if we have a unique solution, every column of A has a pivot. If we have a transformation that is not one-to-one, distinct vectors in X may have the same image T of X. So you can see in our diagram, these two vectors have the same image T of X, but the other two vectors have different images. This means that A of X is equal to T of X or B does not have a unique solution. This also means that if we do not have a unique solution, at least one column of A is missing a pivot. I've taught linear algebra for many years, and this is one of the hardest concepts to explain and also for students to grasp. Let's now look at onto transformations. If we have a transformation that is onto, every vector b, or t of x, is the image of some vector x. That means that a of x is equal to t of x or b has a solution for all b. This also means that every row of A has a pivot. Likewise, if our transformation is not onto, not every vector b or t of x is the image of some vector x. This means that we could have a vector b or t of x that is not the image of a vector x. Let's put a star by this one. This means that a of x is equal to t of x or b does not have a solution for all b. This means that at least one row of A is missing a pivot. Let's now put this into practice to determine if t of x, given here, is one-to-one, onto, both, or neither. When we decide if a transformation is one-to-one or onto, we really have to look at the standard matrix for the linear transformation, which is matrix A. So let's write down what matrix A is. So A is going to equal 3, 1, 5, 7, 1, 3. I always tell students that when you see a comma in a transformation written like this, that indicates that you're going to a new row. And we need to look to see if every column has a pivot or if every row has a pivot. So what we're going to do is we're going to take matrix A and we're going to put it in echelon form and check pivots. So what we're going to do to start is let's switch rows 1 and 3 so we don't have to have fractions. Now we can work off of this leading entry and we'll get zeros below it. So if we multiply the top row by -5, add it to the second row, we get 0, and then -15 plus 7 gives us a -8. Likewise, we'll multiply the top row by -3, add it to the third row, and we'll get 0, and then -9 plus 1 is -8. We see we have a repeat row, so that means the bottom row is going to go to 0. We can think of multiplying the second row by -1, adding it to the third row. And there we go. So let's go ahead and let's highlight our pivots or leading entries. And we can see that we have a pivot in every column. So that tells us that our transformation is 1 to 1. However, we are missing a pivot in row 3. So that tells us that our transformation is not onto. So let's write that as no pivot in row 3. So that tells us our transformation is not onto. I would suggest that you go back and review all these concepts. We went through a lot of concepts, and redo some of these example problems till you're comfortable with them. The next video in the series is going to be on determinants.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.